All right. Today we have evaluation theorem, which is the first part of the fundamental theorem of calculus. I think you learned the second part in Cal 2, but yeah, there's more things to worry about in Cal 2. All right. So all evaluation theorem says is that we can evaluate an integral on some interval AB. So here is our formula. The integral from a to b of f of x dx will be the antiderivative f of x evaluated on that interval a to b. And in order to do that, well, we say f of b minus f of a. There is no longer a constant of integration. Yeehaw. When using evaluation theorem. Okay. So everything below are the formulas that we had last time, all the antiderivative formulas. And let's go ahead and get started. Okay. Number one. Oh my goodness, my email is blowing up. Okay. So here we have the integral from 0 to 10 of 4 dx. Well, we know that 4 is a constant, so the antiderivative of 4 is going to be 4x. But now we will evaluate it on the interval 0 to 10. So what we'll write is 4 times 10 minus 4 times 0, and we'll get 40. And of course, what you are finding is the area underneath a given function on this interval. So if we look at this, this is actually y equals 4, which is, of course, the graph of a horizontal line. But here, we are evaluating on this interval, 0 to 10. So what we're doing is finding all this area underneath the function on that given interval. Well, it just so happens that this makes a rectangle. Not all of them will make rectangles. Well, we can get deeper into that, but here we see that the length is 10 and the width is 4, and the area of a rectangle is length times width, which is also going to be 40. So what we found was that all of this area is 40 units. Pretty cool, huh?
So cool.
Right, there you go. I was looking for those thumbs up. Oh man, my running career is over. I pulled something today. Think
What'd you do?
I hurt my left calf, or below it, I don't know, some part of the tendon. I was running and everything felt good, and then all of a sudden it was like pow. I was like, oh god, well, that hurts. So yeah, and I had a limp all the way home.
Sorry.
It's okay. It's okay. I was like, let me just walk it off. It started feeling better, and I was like, huh. I wonder if I just like cramped the muscle, but it's really sore now. So I guess I'll just sit here and not work out anymore.
It's okay.
Oh,
Yeah, because
okay.
running is definitely the only type of workout that you could do.
I know. I go skateboarding and bicycling and lifting up a 25-pound toddler.
Do that a few times, you'll be good.
Yeah. All right.
Curler with your toes.
There you go. All right. So next is the integral from 0 to 6 of x squared dx. Well, the antiderivative of x squared is x cubed over 3. And we evaluate this from 0 to 6. So here we'll have 6 cubed over 3 minus 0 cubed over 3. And 6 cubed is what? Is that 216? Sure. I think so, right? Yeah,
Hold
yeah.
I should
Get-
know this.
Get the calculator.
All I deal
Calculadora.
with is with binary. Hold up. It said 2 to the 16.
6, no, 6 cubed.
Oh, okay. Thank God.
It's 216. All right,
Yeah.
we're good. All right. And now 216 divided by 3. You guys want to see a fun trick? What's 21 divided by 3?
7.
7. What's 6 divided by 3?
2.
There we go. Look at that.
Didn't you just do long division?
Nope, not at all. What was that? What was it? Three Stooges joke? 7 times 13 is 28.
Oh yeah.
That
And he was like,
pretty
add
cool.
it together.
Yeah. And he's like, all right, you're hired. Hey man, it all made sense. What was it? It was like 13 and 7. He's like, well, 7 times 1 is 7, and 7 times 3 is 21. That's 28.
Yeah, it was something like that.
And then they did the division and he still got it. I was like, oh boy.
Yeah, he was like, 7 can't go into 2, so put that 2 in your pocket or something.
Yeah.
Like, save it for later.
Save it for later. All right. Everybody good so far? All right, fine. Okay. Next. The integral from 1 to 4 of 5x plus 3. All right. So the antiderivative of 5x is going to be 5 times x squared over 2 plus the antiderivative of 3 is 3x. And we're evaluating this from 1 to 4. Okay. So just plug in and I'll get, oh, I can make it look prettier. Hang on, just a little bit prettier. 5 halves x squared plus 3x from 1 to 4. And now plug in 4 and plug in 1. So 5 halves times 4 squared plus 3 times 4 minus, and we're going to need to put parentheses around this one, 5 halves times 1 squared plus 3 times 1. All right. And what's that? 5 halves times 16 plus 12 minus 5 halves plus 3. And that is 2, that's 8, that's 40 plus 12 minus, just change that to decimal, 2.5 plus 3, 5.5. And 52 minus 5.5 gives me 46.5. Yeehaw. Okay. And again, if you were to look at that area, just another visual, right? 5x plus 3 would look something like, what would that be? Probably like up here, something like that. And then from 1 to 4, so here's 1, here's 4. We are finding all this area underneath that given function. Okay. Oh, and like I said, did Jerry teach adding up the rectangles, taking the sum, or no? Or does he just touch on it?
Yeah, he tells him that's how it creates the area.
Because there is a finite amount of rectangles down here that if you found all their areas, they would add up to 40 around 46.5. It's never perfect, but now that's pretty cool. But that's not for a while. It's like, I don't know who teaches the like definition anymore. Or we just completely plug and chug.
Yeah, I think he touches on Riemann sum too.
But it's not really, I mean, yeah. Like you'll teach that theory if you're going in that route, you know?
Yeah.
No reason for engineers to know that.
Yeah.
All right, cool. All right, here we have the integral from 0 to 1 of e to the x. Well, the antiderivative of e to the x is e to the x, which we evaluate from 0 to 1, which means you'll get e to the first minus e to the 0th, and we'll get e minus 1, which is, what's that, 2.78 minus 1, 1.718. There we go. Okay. Everybody good so far?
Yes, sir.
All right. Five. The integral from 1 to 2 of 1 over x dx. Well, we know that the antiderivative of 1 over x is going to be the natural log of the absolute value of x from 1 to 2. Now we see that these numbers are positive, so this means we can actually drop the absolute value. So just evaluate and you'll get natural log of 2 minus the natural log of 1. And then natural log of 2 is 0.693. That's because the natural log of 1 is always what value? Nobody? All right.
0.
0. There you go. Okay, cool. Next. 6. The integral from -2 to 2 of x cubed plus 7x. All right. So we know that the antiderivative of x cubed is x to the 4th over 4. Plus the antiderivative of 7x is 7 times x squared over 2 from -2 to 2. All right, let's evaluate, make it pretty first. 1/4 x to the 4th plus 7/2 x squared from -2 to 2. And plug in 2, 1/4 times 2 to the 4th plus 7/2 times 2 squared minus, and start with the parentheses, we're going to need it, 1/4 times -2 to the 4th plus 7/2 times -2 squared, close parentheses. All right, here you'll get 1/4 times 16 plus 7/2 times 4 minus 1/4 times 16 plus 7/2 times 4. Did anybody see what the answer is going to be? Is this the same as that?
Adolfo put it in chat.
Oh, I see it. Very nice. Since they're both the same, then yeah, all of that adds up to 0. How can the area be 0? That's something to ponder, right? All right, all good? Next. Integral from 2 to 5 of 2x plus 9. All right. Start with the integral of 2 to the x, which is going to be 2 times x squared over 2, plus the integral of 9, which is 9x from 2 to 5. Clean up. X squared plus 9x from 2 to 5, and evaluate. 5 squared plus 9 times 5 minus 2 squared plus 9 times 2. And then 25 plus 45 minus 4 plus 18. What's that? 70 minus 22. So 48. All right. Not bad. Okay. Good on that one.
Yep.
All right. Again. 8. The integral from 2 to 3 of 6 minus x cubed. All right. So antiderivative of 6, 6x minus antiderivative of x cubed, x to the 4 over 4, evaluated from 2 to 3. Okay. Make it look pretty. 6x minus 1/4 x to the 4th from 2 to 3. And evaluate. 6 times 3 minus 1/4 times 3 to the 4th minus 6 times 2 minus 1/4 times 2 to the 4th. Yes. Okay. So here we get 18 minus 1/4, 3 to the 4th is 81, minus 12 minus 1/4 times 16. And that's 18 minus 81 over 4, 20.25 minus 12 minus 1/4 times 16. That's 12 minus 4, so 8. Okay. And then 18 minus 20.25 minus 8, we get negative 10.25. Woohoo. All right, all good? Sweet. More. Okay. Right. Integral of 1 to 2, from 1 to 2 of 2x to negative 2 minus 3. Right. Start with the antiderivative of 2x to the negative 2. That's going to be 2x to the negative 1 over negative 1. And then the antiderivative of 3, 3x from 1 to 2. All right, make it look pretty. I'm going to move the negative to the top on this first one. Negative's going up with a 2 and swinging the x down. All right, so negative 2 over x minus 3x. And now evaluate. Negative 2 over 2 minus 3 times 2 minus negative 2 over 1 minus 3 times 1. All right. So negative 1 minus 6 minus negative 2 minus 3. Negative 7 minus negative 5 plus, we get negative 2. All right. All right. 10. The integral from 1 to 4 of 3 square root of x dx. So we know that we have to rewrite this as the integral from 1 to 4 of 3x to the 1/2 dx. And then now it's in its proper form, we can find the antiderivative. And you're going to get 3 times x to the 1/2 plus 1, which is going to be x to the 3/2 over 3/2. Evaluated from 1 to 4. All right, make it look pretty. Flip that fraction. We're going to get 3 times 2x to the 3/2 over 3. Evaluated from 1 to 4. One more time to make it look pretty. Our 3's cancel. And we get 2x to the 3/2 evaluated from 1 to 4. Okay. Evaluate 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. All right, what is 4 to the 3/2 going to be? We get 8. Okay, so well, that's just that, right? So that's going to be 2 times 8 minus 2. So 16 minus 2, we get 14. Perfect. All right. Everybody good with those two? Thumbs up. All right. All right. Not bad, huh? Okay. 11. We got some cleaning up to do. The integral from 0 to 1 of x times the cube root of x plus the fourth root of x dx. Okay. So we have to rewrite this 0 to 1 of x times x to the 1/3 plus x to the 1/4 dx. And then distribute the x. We have the integral from 0 to 1 and x times x to the 1/3. That should give me x to the 4/3 plus x times x to the 1/4. That should give me x to the 5/4 dx. Okay, now we have everything in its proper form. We're ready for the antiderivative and power rule on both. So x to the 4/3 plus 1. That should give me x to the 7/3 over 7/3 plus x to the 5/4 plus 1. That should be x to the 9/4 over 9/4. Evaluated from 0 to 1. Okay. And now flip both fractions and we get 3x to the 7/3 over 7 plus 4x to the 9/4 over 9 evaluated from 0 to 1. Okay. And now evaluate, and we'll get 3/7 times 1 to the 7/3 plus 4/9 times 1 to the 9/4 minus, and all of this isn't going to matter because it's going to become 0, right? So the whole right side is 0. So we are just left with 3/7 plus 4/9, and you get yourself a common denominator between 7 and 9. So that's going to be, yeah, just multiply that by 9 over 9, 7 over 7. We get 27 over 63 plus 28 over 63 and 55 over 63. Cool. So much fun. All right. Everybody good with that one? All right, good. Okay, then here is the last one for the rest of our semester. We made it, guys.
Whoa.
Woo! All right,
Celebration emoji.
there you go. But this is incorrect. It can't be the integral of y with respect to x, can it?
change the D's to partials and you're done.
Oh, Jesus. All right. Okay. So here we go. We have some cleanup to do, of course. So here's the integral from 1 to 4. And we see we have two terms in the numerator over the same denominator. And I'll first rewrite this one, square root of y, as y to the 1/2 over y squared minus y over y squared dy. Okay. And then more cleanup, the integral from 1 to 4, y to the 1/2 over y squared is going to give me y to the negative, what's that, 3 halves. Yes. Okay. And then minus y over y squared becomes 1 over y. Remember, we don't rewrite this as y to the negative 1 because you'll run into an error. Okay. So there it is. We're set up. We're ready to go. Power rule on both. And the antiderivative of y to the negative 3 halves, that's going to be negative 3 halves plus 1, should give me y to the negative 1/2 over negative 1/2 minus the antiderivative of 1 over y is going to be the natural log of the absolute value of y, evaluated from 1 to 4. Clean up. I'll rewrite that as negative 1 over 2. Flip it, and I'll get negative 2 over the square root of y. So that 2 goes up, and then that y to the negative 1/2 comes down, becomes a square root, minus the natural log of the absolute value of y from 1 to 4. Okay. And now let's plug in. Negative 2 over the square root of 4 minus the natural log. And since these both are positive, we can again drop the absolute values. So you'll just get the natural log of 4 minus parentheses negative 2 over the square root of 1 minus the natural log of 1 and clean up. Negative 2 over 2 minus the natural log of 4 minus just negative 2. And then negative 1 minus the natural log of 4 plus 2 gives me 1 minus the natural log of 4, which could be a good answer unless they want decimal. 1 minus the natural log of 4, negative 0.386. Done and done. Woohoo. And that is evaluation theorem. Any questions on these notes? Everybody good?
Yeah, I think so.
It's not too bad, right?
Mm-mm.
Okay, so these are done.